quasi-periodic linear Schrodinger and wave equations.
Okay, thanks a lot. I'd like to thank for the opportunity to give this talk, and I'm very glad to be here, I must say. So let me start. So I'm talking about reducibility for linear quasi-periodic systems, and let me tell you, start by explaining the equations. So the first thing is the equations. And the Schrodinger equation has the following form: I times delta u. I never know if it's what is the sign of this. Omega t times dot times u. This is the Schrodinger. And the wave equation is a second order equation which looks like this. Dot times u. So this is the wave. Let me tell you what this is. So V is supposed to be a potential here with periodic boundary conditions. So it's a potential on a d-dimensional torus, and it has quasi-periodic time dependence. So V is a function from Tn cross Td into R, and it will be real analytic. The variables here are phi, and these are the space variables of the Schrodinger equation. And omega, which is the frequency vector, it's supposed to belong to some open subset of Rn. Yeah. So this is the setup. We have a Schrodinger equation, we have a wave equation, linear one, with quasi-periodic time dependence. And I am not able to say anything about these equations for a fixed frequency, Diophantine frequency, but we'll say something about it for a large set of frequencies, which depends on the potential. So this is the equations. Now I had a second part here where I wanted to explain that these are the Hamiltonian structure. Sorry?
Oh, this is, oh, wait.
Yeah. So the Hamiltonian structure of this, but I realized that I will not have any time really I will not be able to come to the end. If I do this, I just skip this, and I go over right away to a third part, which is the description of these as quasi-periodic co-cycles. Yes? Omega is irrational? Well, I will choose omega in my open set as so. Yeah, for sure. No. I'll state something about the large set of omega. So, so the co-cycles here. What you do is that you write your objects in Fourier coefficients. Ua e to the I a x, and then of course you write v also. There is no v here. Yeah. Yeah. Sorry for this. I must introduce my v here, otherwise I will be confused. So, well, the right way to see these as Hamiltonian equations is, of course, that you write, for the Schrodinger, you write it as y delta u plus v times u, and the conjugate variable is called v, and that simply verifies the equation delta v times capital V times v. So these are the two conjugate equations, and they are the complex conjugates. So this is for the Schrodinger. And for the wave equation, you do as usual. V is u dot, and v dot is delta u plus v times u. Now I got my v here.
Now you have sigma there, but like
Sigma? No, there should be no sigma. It's a V. Huh? So now I got my V. Now I have my U and my V. Now I can come to my cocycles. Cocycles. So what do? I write U in Fourier coefficient. U hat A e to the I ax. A runs over the d-dimensional lattice, and I write Vx in the same way. Now, so for the Schrodinger equation, you just take now for the Schrodinger, you just take Q to be the Fourier coefficients of U and P to be the Fourier coefficients of V, and then you can write the system as Q dot times P dot equals I times D 0, 0 minus D plus epsilon. You get it A omega T 0, 0 minus A omega T. So this is now a linear system QP. And D here is a diagonal matrix, DAB, which has basic just H, norm of H square on the diagonal. And A is just the Fourier coefficient of the potential V with respect to the space variables. So this is how you write it. This is a diagonal matrix, constant coefficient, and here sits the Fourier coefficient of the potential. So you notice here that what you have is that you have exponential decay in the distance a minus b, because this is supposed to be analytic. They are Hermitian. And you also notice that A is a convolution operator, what we call tuplets. Somebody was once contesting this notion. No, I know that. That's what I put it. That's why I put it in between. Well, so it has translation invariance. So if you replace A by A plus C and B by B plus C, then this does not change. And this is a Hamiltonian system because you notice that the right-hand side equals, well, just the standard symplectic matrix, standard involution, times something which is Hermitian. Yeah. So this is a cocycle. It's a huge matrix, which is diagonal. This object on the diagonal plus a perturbation. For the wave equation, it's somewhat similar, but wave. So after some linear transformations, change of variables in the Fourier coefficient, then you can write it in the following form: Q dot P dot equals I times D 0, 0 minus D, just as in this case, plus epsilon times this matrix. Like that. And in this case, D is still a diagonal matrix, but now it has the norm of A on the diagonal, not the norm squared. And A is almost the same. It is just the Fourier coefficient with respect to space for the potential, but now it has an additional factor, and that is square root of A over B. 1 over A times B.
I'm sorry, probably where does the epsilon in the original equation? The epsilon is just in front of the notation?
Yeah. Here it is. All right. Here it is. Okay. And A here, bracket, is just the maximum of the norm of A and 1. So it's the norm of A except when A is 0.
So epsilon is your coupling constant?
Yeah,
Which you assume to be small?
for sure. For sure.
And those little a's that you got talking, so the little a's are just the eigenvalues, or
No, little a's are the lattice points.
just the lattice points?
Yeah. Little a's are the lattice points. Okay, other questions? Okay, so what we see here is, again, exponential decay in A minus B. You see that they are Hermitian, the matrices. And you see here that A is what we call smoothing, huh? Because it has a decay. When you go far out in the lattice, it's decaying. Huh? So this is the difference between this one of the difference between the Schrodinger and the wave equation. Well, the eigenvalues are absolutely different, and then there is the fact that here we have the tuplet structure, and here we have a smoothing. This is also a Hamiltonian system, but during this change of variable, we have changed the symplectic structure. So the right-hand side here is I 0 0 minus I times Hermitian. Okay.
But you're losing the dispersion again this one.
Well, yeah, that's at least.
Without the smoothing, this is essential for you,
Yeah, for sure, for sure. So I'll explain that, where it comes in. I would be happy to have more smoothing. So let me talk about reducibility. Okay, so what we are studying is a co-cycle of this form, diagonal something plus a perturbation that depends quasi-periodically on time. Huh? So this is what we are interested in. And the reducibility means that you can solve the following equation. You are looking for a big matrix, which depends on the angles. And you take the derivative of each matrix element in the direction omega. Directional derivative in omega should be equal to d plus epsilon a of phi times c of phi minus c of phi times d plus epsilon some d prime, which will also depend on epsilon. So this is a partial differential equation on the torus. It has two unknowns, c and d prime, so it's slightly nonlinear. And the fact is that if you can solve that, then you see that this is equivalent to the fact that the solution of this equation has the form c omega t, something quasi-periodic, times e to the d plus epsilon d prime times t. So these are Floquet type solutions. Huh? And if this guy here is pure point, then you really get Floquet type solutions here. And moreover, if the spectrum of this guy is purely imaginary, then all solutions to this object is almost periodic, quasi-periodic or almost periodic, because they are just linear combinations of these guys. So this is the reducibility. There is a weaker notion also, which we call almost reducibility. Almost reducibility is almost the same thing. So for all epsilon prime positive, there exists this transformation C, which now is allowed to depend on C prime, which says that you can solve the following equation. You can solve the equation up to any order of approximation. d plus epsilon a of phi times c minus c d plus epsilon, a new constant part, and then something which still depends on the angles, but which can be made arbitrarily small. Of course, in general, the norm here is usually a bit weaker than the norm here. So this is almost reducibility, and it tells you then that your system has solutions which behaves of this type for arbitrarily long time. Okay. So maybe I tell you now what is known about this, and I think I'd like to tell you what is known in finite dimension first. And let me talk about SO3R, because this is the one where you have the most complete result. So what we are looking at is a 3x3 system. Real, antisymmetric. We are fixing a frequency omega in the Diophantine class kappa tau. K omega bounded from below by some kappa, k to the norm minus to 1 over norm of k, and this is supposed to hold for all k in the n-dimensional lattice in the Fourier modes. And then you assume that A is bounded by 1 in some analytic norm. Typically, you take, it lives on the torus, and you take the sup norm over some complex neighborhood of the torus. Now, the following theorem is known about that, and that is a joint effort by Claire Chavaudré, Raphael Krikorian, and myself, and it says the following: if the perturbation is sufficiently small, which only depends on the Diophantine class and the analytic norm, then, let me call it, yeah, here is the co-cycle we are studying. Then all A, no, I would like to say that. The co-cycle is almost reducible for all A in this domain. Second is that the co-cycle is reducible for almost all A. And the third statement is that the co-cycle is non-reducible for generic A in this set. So let me tell you what this means. Almost reducibility for all, that has been explained. For almost all means that you look on typical one-parameter families, and then it's reducible in good one-parameter families for almost all parameter values. Generic here is topological in this topology. So it means that topologically things are non-reducible, but the typical thing in a measure theoretical sense is reducible. So it's like the Liouville numbers and the Diophantine numbers. So, and this is what has been proven, so to say, for SO3R. There are little doubts that this is true for all linear finite dimensional systems in the analytic category with Diophantine frequencies.
What if epsilon isn't small?
Sorry?
What if epsilon isn't small?
Very little is known, except in one frequency case, well, I don't suspect anything. Now, in one frequency case, there are, of course, results, new results, by renormalization theory of Avila, Krikorian, etc., etc. So the local picture in one frequency case. local pictures, the global pictures looks like the local picture with certain variations, which they have explored.
It always looks like this.
Yes, except that it may not be reducible to constant coefficient, basically. Typically, it's reducible to constant coefficient or to some rotational matrix in SO2. So there is a lot of global results. The global picture is fairly well explored for one frequency systems, but not at all for several frequency systems.
And you said, sorry if I misunderstood, that your epsilon depends on
On?
A?
No. Epsilon only depends on the Diophantine class, kappa 2, and the analytic norm. So, nice neighborhood of the constant coefficient systems for which you have this structure. So this is the behavior of a reducible system, and there is no reason to assume that in infinite dimension it should be less complicated. Yeah?
So for other groups, it should be true also?
Yeah. It should be true for any system. Yeah. Now, this is a compact one, so let me mention one more result. This is a compact system, so what we really prove is that the generic system is uniquely ergodic. In TD cross as a system in 3D cross SO. This is what it was. So let me tell you what this implies in particular. Now, in SO3R, if you look at the co-cycle here, then the solutions are restrained to the unit sphere. So this implies in particular that if you start by an initial value, which starts in this state, then for some t, you will have that the solution is close to this state. And for some other t, the solution will be close to this state. And it will go close to any state. Of course, typically it will take quite a lot of time to go from here to here. So we have a small perturbation. But on the other hand, if you look at the average on a lifetime, then this solution or any other solution will spend as much time in the neighborhood of that state as it spends in the neighborhood of that state. So that's the statement of the unique ergodicity. Okay, so this is the situation, and that's probably true also for any compact group.
So this is an ODE now?
Yeah, this is an ODE. Yeah, I mean, the other one we have transformed them to an ODE also, but of infinite dimension. So this is the ODE now, co-cycle ODE in finite dimension. And as I explained to you, the wave equation and the Schrodinger equation, we can think about them as the same kind of object, but now in infinite dimension. So let me tell you about the Schrodinger equation. So this is a theorem by Sergei Kuksin.
Techniques for 1 and 2, KM techniques?
Yeah. So same thing. Yeah. And myself, and it says the following for the Schrodinger equation, that if epsilon is sufficiently small, then there exists a subset U of epsilon, depending also on the system itself, of good frequencies. It's a large set, because in measure sense, because the complementary thing goes to 0 as epsilon goes to 0. Lebesgue, some kind of fractional power of epsilon, such that for all omega in this good set of frequency, the co-cycle is reducible. And it's reduced to a constant coefficient, matrix or operator, which is a direct sum of finite rank operators. So with a pure point spectrum, contained in the imaginary one. So you can, so for the Schrodinger equation with good frequencies, all solutions are almost periodic. We don't know what happens with the remaining part. Are we here or are we here? Huh? Or something else. So this is a theorem. Now, for the wave equation, I only have a conjecture, which is based on joint work with Benoit Grebert and Sergei Kuksin. And it says that the same thing is true. With one possible exception, that is that there may be a small part of the spectrum in the wave for the wave equation which lies in R. That's not excluded.
But the conjecture is an understatement. Basically, it's just a matter of writing it down.
I tell you what. I'm going to talk about this now. So let me see. What do I have as
Do you
time?
have examples where you do get real spectrum? You said the same is true, except perhaps that there may be real spectrum.
No, I don't have an example, but I will be ready to construct one. Okay. So this is the background. Now, what I would like to talk now about is the ideas and what we have behind this kind of stuff. And I think I'd like to stay on the big board. So let me take this away and continue here. So what this is all about is something called the second Melnikov condition. I think I have 5. Second Melnikov condition. I like to condition. So we like to solve the equation for reducibility and hoping that it is perturbative. So you like to construct a matrix C of phi, which we write as e to the epsilon x of phi, which is identity plus epsilon x plus higher order, and which will be small if we have some good control on the norms here, on the size of this. And then you plug this, you linearize the equation. Equation for the reducibility, and what you get is a linear equation which is derivative of the matrix x of phi in the direction omega should be equal to d commutator with x of phi plus a of phi minus eventually a small correction. And let me assume, to simplify a little, it's not essential, but let's assume that my matrix here, D, is diagonal with diagonal elements, which I call lambda of A. Could be parametrized over the whole lattice, or it could be a finite dimensional system. So now if D is diagonal, then this equation splits as one equation for each matrix element. One equation that depends on phi, and then it becomes one equation for each Fourier component. So the matrix element xa of b, its kth Fourier coefficient is this, and it is equal to the corresponding matrix element here, the corresponding Fourier coefficient. You have to correct for this possibly, so d prime a of b, but only for k equals 0, because we don't, or hopefully we would like to do that. And then you divide it by the small divisor, which is k omega minus lambda b minus lambda a times I. So
These are canonical transformations, roughly speaking, is that right?
canonical transformation.
You're making a change of coordinate to diagonalize this.
For sure. Huh? And well, since we write it in this form, I mean, if we got an x in the Lie algebra, we get a transformation in the Lie group. Huh? So what we need here, you see it right away, that of course this is not allowed to be 0. And in order to get a bound on these, what we need here is some lower bound for the small divisors. And this is what is usually called the second Melnikov condition. What do we want it? Well, we would basically, we can, if this is very small, we can admit that this is very small, but it should be bigger than this. So it should be much bigger than the norm of A, B, and K. So square root of that would be great. Huh? And let me recall now that we have exponential decay of this in A minus B. We have exponential decay in K of this guy. So it's when K is large, it's very small. When A and B are very separate, it's very small. And also for the wave equation, we have, in fact, also small when we have decay as square root of A times square root of B. This is what we have. So that is what we want to prove. Huh? We'd like to prove some estimate of this. Of course, you cannot prove it for anything. Huh? So there are, of course, exceptions. And the most obvious is, of course, A equals B, K equals 0. But there may be others. Huh? May be others. And moreover, since this is multi-scale analysis, once you started with D, at one moment you must also consider D plus epsilon D prime. So we'd like to need this also for perturbations of these eigenvalues. Huh? Not only for the original one, but also for the perturbed ones. Also for perturbations of lambda A and lambda B. Huh? All perturbations would be great, but at least all perturbations that will appear in your multi-scale analysis. Huh? So this is the stuff. And of course, the perturbations are not known a priori. Huh? So let me tell you what is the known about this for the Schrodinger or what we proved. So for the Schrodinger equation, it looks like this. And we like to have something which is exponentially decaying in K, exponentially small in A minus B, and then some kappa. Because here we have no smoothing. And then you see that the exceptions are, in fact, just A minus B, norm of A equals norm of B, K equals 0. That are the necessary exceptions. And in fact, by a good choice of omega, you show that these are the only exceptions.
Good thing that you have integers there, right?
Yeah. Yeah. This is, of course, easy. I mean, because finally, these are integers. So they don't, even if there are many A's and B's, they don't take so many values. Huh? So that's easy stuff. What is less easy is also that this remains under perturbations. So you can always choose omega in a big set so that the exceptions to the second Melnikov condition remains this one. And this is the basic thing. Yeah. Okay, voila. The situation for the wave equations turns out to be much more complicated. So that's.
You say that you need to show that it remains under perturbation, but the question is whether after you do the perturbation there are no U exception that.
Yeah, that's what this segment. Only exceptions are this, if you choose omega appropriately, and this is still true. That's the main part of the work, I would say, to prove this. And that uses strongly what we call the Toeplitz property of this system. Now, let me describe you the obstructions to the Melnikov condition for the wave equation. Obstructions to second Melnikov for the wave equation. So what is at the starting point, we have these guys here. And I think the best thing one can hope for is something like that. E to the minus rho of k, that's fine. E to the minus gamma a of b, that's also fine. And then I think it should be something like that. 1 plus something. I think that's the best thing you can hope for. At least we haven't been able to prove anything better. And even we had, I have strong feelings that that should be the right thing. Maybe you know that. So this would be fine. This would be fine if we had a sufficiently smoothing system. Then
what's the difference? I see the difference is you have the squares, and this is got, this, I know that's a big difference. You have, you have the linear parts here. You have to take the square roots of the norms. And so those are not integers, right?
Yeah, those are not integers.
Not integers, and you only get one type.
Here.
But I still don't, yes, I understand that. You got squares there.
Yeah, so here, and they can only take integer values.
Yeah, they're well separate. Yeah, they're well separate.
Yeah. K is bounded. So this is bounded. These are, you only have to avoid here in this case, so to first step, integer values, and that's finitely many. While here, you have no integer values, so you have to avoid already at the first step, infinitely many.
Side, they look the same, except I can't read what that kappa over k is, what you have in the Schrodinger case. What is that?
Well, it's just that you say you take some small constant, I mean, so.
Yeah, but then this looks, I mean, the way you've written it looks just as good, that's what I'm saying.
The way I written what?
The way you've written the right-hand side of the inequality.
Here?
Yeah.
Yeah, it is just as, well,
Okay.
it is just as good if this guy is sufficiently smoothing. So here I can get at best this one. And if I have a perturbation which is at least so smoothing, then I would be fine.
Does the dimension help you?
No, does not. But I don't have a potential. From the wave equation, the only thing I know is that I have something which is smoothing with 1/2 here. So if I look at another co-cycle which is more smoothing, then I would be fine. But now I'm interested in the wave equation.
Maybe you should have said you are in dimension 2 or higher, right?
I am in dimension 2 or higher.
Yeah, I was just asking if sometimes very high dimension helps because.
Yeah.
So
No.
dimension 1 is much easier.
Yeah.
Yeah, I used to be not.
So I like to. So if I like to put something here rather 1/2, then I will necessarily have obstructions to this. There are necessarily obstructions.
Yes, my question is, you don't have that term, that last factor on the right side in the Schrodinger.
No,
And
no.
you don't need it.
You don't need it.
You don't need it.
No. I mean, we don't have it, and that's, well, we prove it that we don't need it. Yeah.
And here you need it.
Here I need it, at least. I don't know if you can prove anything. I mean, come on, I'm trying to prove something with smoothing. I mean, this kind of smoothing. I mean, come on, you ask me if I can prove something without smoothing. Well, I don't know. I'm happy to prove something for this. So this is what one would like to have, and if you have this one, then you will necessarily have a lot of obstructions to this kind of condition. So let me describe them to you. So first of all, I will need a Diophantine condition. Let me prove it here. Another Diophantine condition, which we called omega twiddle, DC twiddle kappa of 2. So what is it? Well, it says the following. For all j in between 1 and d, which is our lattice dimension, for all j tuples of Fourier vectors in Cn, for all j tuples of lattice vectors, you look at ki omega times kj omega minus ia ei ej. That's a symmetric matrix. This is a symmetric matrix, capital J by J matrix. You look at the determinant of this guy, and you say it should be bounded from below by some kappa, and then you take k1 plus kj, add 1, because I want to include the zeros, and then you take e1 plus ej, and you put everything in the denominator with a big potential. So this is my Diophantine condition. So I tell you what it looks like when j equals 1. Then it just says that k omega squared minus e squared, which is an integer, is bounded from below by kappa 1 over k plus 1 times the norm of e, which in this case should not really be necessary, to the power of 2. So that's what comes in j equals 1, which is somewhat naturally because we are discussing the wave operator where there is a second derivative. So, but this is, so to say, the generalization of this guy to higher dimension.
Is it obvious that there are many omegas which set? I mean,
Yeah, I'll prove that. I prove that. So if you, if you take t to sufficiently large, this is a set which is small. For some reason or another, I think it was small sk to the power 1/4 or something like that, but not small. Yeah, no. It's a big set. Yeah.
Excuse me, it's supposed to be inverse, the sum.
Yes. Thanks. You put it in the denominator with a high. Yeah. Okay. So I like to continue on here.
So are you saying this condition is sufficient for your purposes then?
I'll tell you what it gives us for the obstruction to this second Melnikov condition. I'll take it out. I will not have the time to go through the proof of that in any case. So no, I just wanted to tell you, just wanted you to see it. So. So the proposition here is the following. I will implicitly assume here that tau is bigger than the 2 dimensions here. I don't want to talk about that any longer. So let me see that I get the statement right. So you assume, first of all, that your omega is in this Diophantine's class, and I don't think, the way I've written it, it does not necessarily imply that it satisfies the original Diophantine condition, so I add that also. And then it says the following: for all mn, which are just numbers, real numbers, bigger, I will also consider a beta, which is smaller than 1/2, and it should be quite close to 1/2 by some constant, which is 1 over tau square or something like that. So it should be 1 over tau square close to 1/2. So we put us really close here. Then there exists a partition, script E, of the lattice CD. The partition elements have a bounded diameter. The partition element that contains A is bracket of A, and they all have a bounded diameter, which is some universal, well, universal, depends on tau here. It is m to the n times A to the, now I change, I will say 1 minus 2 beta to some exponent, which also only depends on tau. So they have some bounded, no, it's not there, in fact. Well, it is the diameter of this. So we have a partition of the lattice into finite dimensional pieces. And for all partition elements, there exists a mapping MA, which goes from the partition set into the set of Cn, which are where the Fourier modes are, and it takes an A to M of A. So it's well defined for each, so you have it everywhere. Such that for all AB in our d-dimensional lattice and K in the Fourier modes, then the following is true. Either distance of these two blocks is bigger than m, we have fixed m, we have fixed n, we have fixed beta here. So either, and when I talk about the distance, I mean the minimal distance between the sets. Or K is bigger than n. So either the distance is large, or K is large, or we have K omega minus B minus A bounded from below by something like m times n to some exponent, tau, which you can take as the same as this one, times 1 over A B to the power beta. So you have this, except when you are lying in the same partition set where you have one exceptions. Which is given by MB minus MA. Yeah. So, moreover, if you have B, A plus C, B plus C in the same partition set, then MA plus C minus MB plus C equals MA minus MB. So it's basically some sort of affine mapping or something like that. So let me show you what this means. So it has a rather rigid structure. Oh, let me see. What time do I have? Oh. Yeah. Okay, let me tell you this. No, I don't tell you this. I'll tell you what we use this for. Let me tell you what we use this for. I have 10 minutes. Still have 10 minutes? Yeah, so let me tell you what we use this for. So, this is my 7th part, how to use this. So we fix B here, very close to 1/2. I take m as a to the power s, and I take a and the same. Now, and I take s now very small. And then I construct my partition with this. Now I get a partition which is E. And now we split the Fourier modes into the following set. So our perturbation is now determined by 3 parameters, a pair of space modes and the Fourier modes, and we split them so they are determined by A, B, and K. So we split them into S, which is the set of A, B, and K, such that A minus B is bigger than M, that is A to the power M, which is A to the power S, and K is also bigger than A to the power S. Now, this part of so that takes out, so to say, a part of this matrix. This part is strongly smoothing. That's why I call it S, because they are exponentially decaying in K, they are exponentially decaying in A minus 1, and since K and A are very strong, by paying a little of the exponential decay, you will get a much better smoothing. You pay a little, say half of it. And now you will be in a much better smoothing class. Then you have the obstructions. And that now is the guy I detected here. So these are my obstructions to the, so these are A, norm of A equals norm of B, and K is unique, takes a unique value here. And then we have the remaining ones, which I call G, for good, because they verify a good Diophantine condition. Look here, I have A to the power S, I have A to the power S, S sufficiently small, so it can be eaten by this, so they will verify a good Diophantine condition, K omega minus B minus A, bounded from below by 1 over A B to some power beta twiddle, which eats a little, which is a little less good than beta, but it's still close to 1/2. It's strictly, beta twiddle is now strictly close to smaller than 1/2, but it's close to 1/2. Okay, so we split our matrix in these three things. Now, what do you do with this? Let me continue here. Maybe now. So we have our perturbation, and we split it into this part, where we basically know everything. We split it into the good part, and we split it into the smoothing part. And now we do reductions in 3 steps of this. So first reduction, I think I like to continue here. So the first reduction is completely explicit. You would like to construct a change of variable, and the one you take is this one, phi. It's a diagonal matrix, not close to identity, not even homotopic to the identity. It's a diagonal matrix. And what happens when you transform your system by this, so you look at now part of your system, which is A, this one. And then you compute it. What you get And what you get here and it turns out that when you do the change of variable, d-twiddle, you change here, the time dependence will completely disappear. Because in this guy, there just sits very special, oh no, I've taken it away. Sits only very special Fourier modes. So d-twiddle remains a diagonal matrix, but the eigenvalues change. Huh? This is an illustration of the well-known fact that the Floquet exponents are not unique. Yeah? And by a rotation, you can change the imaginary part of the Floquet exponent quite by elements in the frequency margin. B is now a constant matrix, and it just picks up the particular Fourier mode that stands here, sits in this, and that's all. So that's now realizes a transformation which gets you down here. And then when you just add here R good plus R smoothing, and of course it would just be transformed by this. So what you have here is epsilon R good twiddle and epsilon R smoothing twiddle, and they are just conjugated of the initial one with this transformation. So that's the first step. Huh? Now you have a new one here. Huh? You have a constant one, diagonal, plus a constant block matrix, and now you look at that one, and you do the second reduction. By an iteration. So you now take D plus epsilon B plus the good guys, and you construct by iteration a transformation now close to the identity, which transforms this into a new system and gets rid of this. There's basically no small divisor problem in this, because the divisors are basically bounded from below by a constant. So this will give you D plus epsilon B, may give you some contribution to this also of the same block, so it may give you an epsilon square B prime coming from this one. This is still block diagonal. And then you may get something else, because when you multiply two matrices of this in this one, you don't stay in the same class. So you may get something in the smoothing class. But when you are in the smoothing class, it's small. So you may get something which is C smoothing. And that works perfectly well. Basically no small divisors including this, because you only consider the divisors related to this one, which are bounded from below. Well, they are divided by A, but that's basically the scheme. So this is the second reduction. And now you plug in plus epsilon of this one, which are now strongly smoothing. Yeah? And then you transform that also, and what you get here is now epsilon A twiddle twiddle S. And now what you have reduced this, so you have reduced this to a system which is epsilon B times epsilon square B prime. This is block diagonal and constant. And then you have a perturbation here, which I will call whatever now, F. Huh? And F is strongly smoothing. And now the small divisor condition that I described to you right at the beginning, which was not good for the wave equation, should be good enough. Yeah. Now, let me say two things. So I Einar for 2 more weeks, and we would have been able to finish this. Now we haven't done the 3rd step, so this reduction we haven't done, but that remains to be done in order to complete the, so to say, to prove the conjecture which I announced to you. Now let me make some comments here before I stop, and that is up to this thing here we have not used any frequency selection. We fixed the generalized Diophantus condition, and it works nicely all the way here. Now, when we have to handle this, then we will have to use, well, at least I don't see how we can avoid now using frequency selections here. So that's the 3rd part that remains. Okay, was there anything more I wanted to say? No,
Where's this funny real eigenvalue that you scared of? Where is that
well, basically, I mean, come on. What we are doing is looking at D here for the wave equation, and D is.
I mean, this will be something below the continuum.
No. D is the diagonal matrix here of this one. So 0 is in the spectrum of D. And then, of course, the next one is 1 and -1. And now we perturb it a little, and there is something may come out of that 0 eigenvalue. But that's the only thing that may come out in the real. The other one stays. Yeah. Okay, thanks for your attention.